Are you ready to learn printed circuit board design? I've been designing PCBs for 30 years, and I'm going to share my secrets with you.
Hi, I'm Stephen Chavez. I'm a Senior Product Marketing Manager for Siemens. Welcome to our second video on PCB design best practices, where we'll outline how to optimize engineering productivity and efficiency to reduce design cycle time, reduce costs, and lower risks. So when we talk about PCB design, by utilizing today's horsepower and capabilities, we can significantly optimize the design approach and multidiscipline integration and collaboration to be faster, produce higher quality designs, and lower project risks. So when I talk about productivity and efficiency, automation is the first thing that comes to mind. And when I think of automation, I think of placement, route, and manufacturing output. The problem we typically have is the legacy methodologies can't meet today's design complexities. The typical roadblocks you'll hear is that you're unfamiliar with the automated functions in the tool, you're feeling of less control, or you don't trust the tool. The legacy processes tend to be standard. The best practices for this pillar would be to assign your parts to groups and clusters, route utilizing the combination between interactive and automated routing, and generate your manufacturing outputs utilizing built-in automation functionality. The value you would get from these best practices are you would have shortened design cycle time, you would have an increased layout efficiency, you would have the ability to do what-if scenarios, your reviews would be optimized and more efficient, you'd be able to implement changes more efficiently, and you remove the potential for errors, as well as you'd have consistent manufacturing outputs. Now let's look at an example of automation regarding routing, placement, and outputs.
When placing components in a layout, one way to speed up the process, besides placing reuse circuitry, is by using component groups. While reuse blocks assist in aiding pre-placed and routed circuits, component groups help to keep parts together that may not be part of a reuse block that should be placed near to each other on the board. For instance, in this example, the DDR4 components. Component groups still show the user netline connectivity between themselves and other components, which can help in determining the best place or location for groups of components. They also are sized based on the size of components within them to help determine the board real estate that each group may take up or occupy. When it comes to routing, automation is the key to increasing productivity. While Expedition has a powerful auto router, many times it makes sense to use a more interactive or what-if approach, or a combination of both auto route and interactive routing. Using Sketch Planner allows users to start to plan where routes will go and can even be used before all components are placed. In the example shown, the designer is using Sketch Planner to create blind sketch plans for single pin routes going to a yet-to-be-placed connector. With plans created, the pins can be broken out and routes started. Once the connector is added to the board, using SketchRoute makes quick work of the remainder of the connection.
The next best practice in this pillar is concurrent design regarding schematic and layout co-design. The typical problem that we have today is that the legacy process is a serial approach, which is inefficient. And what I mean by that is we could be doing things in parallel. The typical roadblocks that we'll see is that we're not wanting others to touch the database while we're working in it, or we don't want anybody to modify our work, or there's inefficient work distribution and how we level load to utilize our team members more efficiently. We tend to be working in silos, and there's really no incentive to make a change in the process or how we do things, because we've managed to be successful so far, yet we're not fully optimized that we could be. Now, when we talk about the best practices that would flow into this, would be to utilize advanced capabilities regarding schematic and layout when we talk about concurrency. And what I mean by that is, in the schematic, I could have two individuals or two users or three users. I can have two EEs or three EEs working in the schematic in the project at the same time. I can also commercially have multiple PCB designers working in the layout at the same time. And then to make it even more complex that we have the capability of doing is I can have multiple schematics in the front end, which is the schematic, and multiple designers in the back end working in the layout, everyone working simultaneously in one project at the same time. That's horsepower. When you think about how many man hours you can achieve in attacking your design with multiple users. And these are the best practices that you would want to implement. It allows you to optimize multi-discipline integration in a database, as well as optimize team utilization. So the value you're going to get from this is that you can accelerate design cycle time, reduce development duration and cost, as well as improve design optimization and efficiency with real-time concurrent engineering. You can also enable simultaneous multi-user and multi-discipline contribution. So now let's take a look at an example of concurrent design regarding schematic and layout.
Working concurrently on a design can accelerate design time and reduce product development cost, since real-time concurrent engineering enables multiple individuals to contribute simultaneously to each task. Concurrency during PCB design comes in many forms. The important aspects to being productive is that designers in a team need to be able to work on the aspect of a design that they need to, while others in their team are doing the same, respectively. Using Expedition, designers can be working together in the schematic, the layout, or both simultaneously in real time. In previous sections, we saw users working concurrently in layout while placing components and reuse blocks and while tuning sections of a board. In this example, designers are working on different sheets of a design in the schematic.
The next best practice within this pillar is constraint-driven design. You're designing with rules that you put up front that'll help you create your design correct by construction. And the typical problem that you would run into is that your rules are inefficient, or you have an inefficient implementation of your rules that actually come from your requirements. The roadblocks you see are typical. You don't have time to implement these. It takes too long to implement them, and it's typically the engineers don't know how to do it because it's someone else at a lower level. It would be their job to implement that. So the engineers usually toss it over the fence to ECAD, and whether they get the design rules or not, or get them accurately all in place, there's potential for error. So that's why these are the type of roadblocks you would see. The best practice you're going to get from this is that you create an automated way to manage these constraints. So that way, not only that you would have them in place, but you can use them design after design, and you can build base templates. So that way you're not reinventing the wheel, and all you do is modify whatever design constraint that was for that particular design you were engaging in. As well as it allows you to control your electrical or physical rules that you need for your design. The value you're going to get from it is the fact that you're going to produce quality, or you're going to design quality into your board. You're not going to check for it after the fact. So with these rules in place, you're going to be able to have confidence that you're meeting your requirements. You're also going to have a tool in a way that you can implement the rules more efficiently. And like I said, you eliminate the human factor of having to go back and check your design. It's checking as you're designing the board, real time in process. So now let's take a look at some examples of constraint-driven design.
Reducing manual re-entry of information during a design is another way to improve efficiency. Constraint entry for design in Expedition is done in an easy-to-use spreadsheet-like GUI, which allows cross-probing to the application like schematic and layout. It also has a powerful built-in automation for simplifying tasks such as identifying and assigning differential pairs. These constraints are then available in other areas of Expedition. In the case shown here, the target lengths dialog that the designers are using helps make sure that when tuning these nets, they stay within the parameters laid out in the constraint manager, such as min-max length and tolerances. Notice that the designers are even using the tool in layout to have the traces tuned by the tool instead of attempting to do it manually.
The next best practice in this pillar is design reuse. And I can tell you, design reuse is typically, it's not inherent to a lot of processes within the company. And I say this, if you go to any show, or even if you go to LinkedIn, you talk about design reuse, It's kind of like auto routing. A lot of people don't do it, even though their tools are capable of implementing, they just don't do it. The typical problem that you have is you're reinventing the wheel over and over. You're doing similar layouts of whether it's a power supply or any kind of driver or any kind of FPGA that you've used over and over. You're redoing the same layouts over and over in general. The roadblocks you'll have is you'll have inefficient process for data sharing. So when you want to implement, not just for within your team from design to design, but I'm talking about an enterprise level. And I'm not talking about cut and paste. You're truly treating your design reuse like a component, an individual component, even though it could be a set of schematic, like a 25-page schematic versus just one LAN pattern. A lot of times you'll have engineers that say, well, I have my own power supply I'm going to use. I know, John over here used this one. Instead, I don't trust it. I'm going to use my design. And he could have saved time if he would just reuse the design that was already done. And the biggest thing is that there's no pressure to change. They'll continue to use the same methodology they've been doing over and over because what little success they've had, they feel it's good enough, but good enough could be only like 65%. They're still leaving room for optimization to be better. You want to utilize existing known good circuitry and proven circuitry and proven layouts, so you're not reinventing the wheel. You want to be able to manage the reuse modules no different than you would manage a single component in a library. And then you want to be able to share that hardware IP, not just from design to design within your business unit or within your company that may be in your local area, but if you have a huge enterprise that's global, you want to be able to share that IP globally so that way you could take advantage of designing whole systems a lot faster. And the value you're going to get from that, you're using known good parts, you're using known good circuitry and layouts that have already been proven. And you're going to reduce your design cycle time, which reduces costs and lowers risk. Your IP, you're going to be able to share that at the enterprise level or globally, and then you'll be able to reuse modules and manage them within your library. And it enables you to use the cut and paste method as well as manage your reuse. So let's take a look at a few examples of design reuse.
One of the first ways that comes to mind when thinking about productivity and efficiency for many different tasks is reuse. Reuse has the potential to be a game changer when implemented. With PCB design, the use of known good tested or approved circuits and layouts can reduce design cycle time as well as reduce cost, since IP can be shared throughout the enterprise and across designs. In the case of Expedition, reuse modules can even be created and managed similar to single components in a library. This means that not only are reuse modules shared easily, but with this comes the ability to track which reuse modules have been used where, and in case of the need to modify the reuse modules, which may happen if a part is used in the module that is out of stock or has been recently made obsolete. Reuse is also easily done on the fly by simply copying and pasting circuitry and layouts.
The next best practice in this pillar is advanced design technology, specifically regarding rigid flex and HDI, which is high-density interconnect. Typical problems that we'll see with this advanced technology implementation is that when it comes to rigid flex, a lot of times people just don't know. They're a bit hesitant to go with it, or they don't think it's efficient enough to be able to work in their product that they want to design. When we talk about HDI, the problem is that a lot of people are still using the standard via structure when they could be using HDI. A lot of times the roadblocks they'll run into is that a lot of people are not familiar with rigid flex design or how to incorporate HDI into their design, or even if it's viable for their design when it could be. And a lot of times all it takes is a simple phone call to their fabricator, and you'd be surprised how many people don't talk to their fabricator. People use a standard approach when they could be utilizing these advanced capability or this advanced design features that's out there. When it comes to designing, a lot of times the roadblock is that it requires a SME or a subject matter expert for that, or there's inefficient processes reduce the opportunity to implement HDI. So when we talk about best practices for HDI and for advanced design is utilizing the opportunity for rigid flex methodology within our tool sets that we have that allows a more efficiently way to define a board outline, as well as the stack ups and regional constraints that you would have. Because when you think about a rigid design or rigid flex, you'd have a rigid section, you have a flex section, and then another rigid section. You could have multiple stack ups. In the rigid area is one stack up, and then in the flex area is a different stack up. So a lot of it can cause a lot of confusion, especially if you're not sure, if you've never done it before. But our tools are more than capable of doing this all in one design database versus multiple databases. And when we think about the capabilities that are out there, they're commonly available in our tools today. So we need to stop doing workarounds from tools of the past of what we've been doing, for our legacy designs. When we think about what kind of value do they bring, you have a more efficient way to design complex systems. You have a way of optimizing signal flow from board-to-board connection in a way of eliminating connectors, the ability to implement complex requirements into your design. When you talk about high pin count BGAs and so forth, especially as the pin pitch gets tighter and tighter, sometimes you have no choice. You're boxed in the corner. You have to implement HDI just because you chose a certain pin pitch on a part. It eliminates workarounds, as well as the ability to add complex designs. Like I said, when it comes to your whether it's a connector or an IC, and then you're able to reduce costs and minimize risk. So now let's take a look at some examples of advanced design regarding rigid flex and HDI.
Having native support for technologies like rigid flex can be essential for designs where space is limited. To expedite a rigid flex design, a qualified manufacturing stackup can be imported directly from hyperlinks. These defined layers can then be assigned to different board outlines in the design, which are used to manage the separate rigid and flex regions of the board. This can be done manually or from stackup schemes that have already been defined. For more advanced designs, once the designers have moved on to placement, buried cells can be placed on internal flex layers of the board.
So thanks for tuning in. Keep following along as next time we cover PCB design best practices regarding digital prototype driven verification.